Okay, so this is the solution for Exam 1. So these first two problems, you were asked to choose one of the two, and these were problems focused on drawing Miller directions and planes. So this first one, we were supposed to draw an arrow showing the direction 2 bar 2 1, and that is -1 plus 1 plus 1/2. So if we start here in our origin, we're going to go, actually that's not going to work, we should start here as an origin. If we started on the back, we'd have to trace back behind the atomic plane. So because we have a negative direction in the x direction, we'll start with this as our origin, we'll go back -1, then we'll go in the y plus 1, and then we'll go in the z by plus 1/2. And then draw a vector. Here we're going to draw the plane 2, 0, 1 bar. So in the planes we invert these. So 2, 0, 1 bar becomes 1/2 infinity -1, and these are the intercepts. We're going to intercept the minus z plane, or the axis at -1. Therefore, we should pick an origin which is somewhere on the top face. And these are positive and infinity, so I'm going to pick that as my origin. So that's x, y, z. We intercept x at 1/2, right there. We intercept y at infinity, so it never intercepts. And we intercept z at -1, right there. So that means that we will have a plane that looks like this. Okay, going to this problem 2, this becomes 2/3, 1, 2/3. These are all positive, so we can pick our origin here. We go 2/3 x, we go 1 y, and we go 2/3 z over here. We can draw like that. Here we have the 1 bar 3 1. Inverting that, we get -1 1/3 infinity. So we're going to be crossing the x-axis at -1. So that means we're probably going to want to pick an origin somewhere on this face, and we have a plus and a plus here. So I'm going to pick that as my origin, which means I'm going to have this as my y-axis. This is my z-axis. That's my x. I intercept x at -1. I intercept z at positive, intercept y at positive 1/3. So it's going to be here. And z at infinity, so it never crosses. So that means we're going to have a plane that looks something like this. Kind of a narrow plane as it's drawn, but you can see where it intercepts the axes. These next two problems really we're talking about crystal structure and about packing density. and lattice parameter and diffraction. The first problem gives us lead, that's FCC. We picked a kind of nice round lattice parameter and the atomic weight. So we have the equation rho equals NA over VC NA. If you want to use equations, otherwise you can just work it out from units. It's FCC, so N is equal to 4. A is 210 gram per mole. VC is, I'm going to do this in angstrom, 5 cubed, and NA is 6.02 times 10 to the 23. And when you write that, you get 1.12 times 10 to the minus 23, and that is going to be grams per cubic angstrom. And you can certainly use that as a solution. You get full credit for that. But if you want to convert that to cubic centimeter, it turns into 11.2 gram per cubic centimeter, which is a little easier on the eyes. The question of planar density, this is how many atoms per area in a plane. And we've got FCC crystal, so it's cubic, and we're interested in the 101 plane, or 101 family of planes, so we're basically interested in this plane. And we know in an FCC we have atoms that are going to be on the corners and then in the center of the faces. So this translates into something that looks like this: atoms on the corners and in the middle. So we have 4 atoms shared by 4, so that's going to give us 1 atom from the corner, and then 1 atom, because we have 2 atoms in the halves, so we get 2 atoms per, and this length is still A. This length going across the center of the face we know is square root of 2A. So that gives us A squared square root of 2, putting in 5 squared, we get 0.057 atom per square angstrom. And that's kind of a reasonable unit to use. This next problem, the problem that involves diffraction, and I made this problem so there's kind of a simple step here. The 100 planes, those are the these planes, right? So that means that the d spacing between the 100 is just equal to A. So that's handy. We have excuse me, n lambda equals 2d sine theta. We want to find d because we're given theta and these. So we have A equals d equals n lambda over 2 sine theta And I told you you should use n equals 1, and if I didn't tell you, you should still know to use that. So n equals 1, lambda is 1.5 angstrom divided by 2 sine of 13 degrees. And that gives us 3.33 angstrom. And we're told that we're working with polonium, which means it's a simple cubic crystal, which means we have 1 atom per 3.33 angstrom cubed. And we have the atomic weight, which I can see here it's the wrong atomic weight, but for the sake of having a solution, we put in 210 gram per mole. To get a density, we want this in gram per volume, and we have these moles and atoms, so we have to also use 1 mole per 6.02 times 10 to the 23 atom. Just Avogadro's number. Atoms cancel, moles cancel, and that gives us 9.45 times 10 to the minus 24 gram per cubic angstrom, which you can convert to 9.45 gram per cubic centimeter if you prefer those units. And for the exam, I kept this number, so this is the correct answer on the exam. In real life, you should look up what the correct atomic weight is for polonium. This problem was a problem of, or should I say, these two problems were about defects. This one we were talking about interstitial sites, and basically I was saying if you have an FCC crystal and you have tetrahedral sites and they're all occupied, what is the density of the atoms that are occupying it? Well, we have 8 tetrahedral sites, 2, 3, 4, 5, 6, 7, 8 per 5 angstrom cubed. So we have 8 sites per 5 angstrom cubed, which gives us 0.064 atoms per cubic angstrom. This problem is a problem about understanding the relation between the Burgers vector and the line vector, and the line vector is tangential to the dislocation line everywhere, which means that the place where we get pure edge is where the Burgers vector and the line are perpendicular, here and here. And we get pure screw where they're parallel, which should be here, 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 but also here and here. So we get those 6 screw sites. This set of problems focused on diffusion. They may be familiar to some of you. These look like problems that you've seen before. And for this we use the Arrhenius relation, d equals d0 x negative q over rt. And our first step is to solve for the prefactor. So we have d0 is equal to d over x negative q over rt. Using what we're given, that 1.8 times 10 to the minus 10 meters squared per second divided by x negative 150,000, that's joule per mole, divided by 8.314, that's a joule per mole per Kelvin, times 1,000 Kelvin, so it's all unitless. We get 0.0123, and they have units of meters squared per second. So 0.0123 meters squared per second. Putting that back into the diffusion equation, we get 0.0123 meters squared per second, exp of minus 150,000 divided by 8.314 times, in this case, 100K. And solving that, we get 5.4 times 10 to the minus 81 meter per second, meters squared per second. Should point out, that's 1 times 10 to the minus 81. This is 1 times 10 to the minus 10. This is an absolutely tiny number. That's because we went from 1,000K to 100K. 100K, I mean, that's just barely above the temperature of liquid nitrogen, so it really is a tiny number. Now the next problem, the problem of flux. So this, you use Fick's first law, minus d dc by dx. In this case, we can replace the integral, or replace the derivative with differentials, minus d delta c over delta x, and putting in our handy numbers, we get minus 1 times 10 to the minus 10 times 0.1 minus 1.1 divided by 0.001. Notice I had to transform the thickness in millimeters into meters because our diffusion coefficient was given in meters squared per second. So that's something to keep an eye on. When you do that, notice now we have meters squared per second. Here we have kilogram per meter cubed divided by meter. So this flux, when you do the math, turns out to be 1 times 10 to the minus 7, and it has units of kilogram per meter squared second. And write that in. So we want to know, not the time, we want to know the amount of nitrogen. And that means that we can take kilogram per meter squared second, multiply it by the area that it passes through, and multiply it by the time. You get 1 times 10 to the minus 7 times 1 square meter times 1 times 10 to the 6th second, and we get 0.1 kilogram or 100 grams of nitrogen. And lastly, let's go through these. True or false, amorphous polymer in glasses have a structure of a random arrangement of atoms. That is false. Amorphous materials are not random. They have an order, they just don't have a long-range order. Diffusion of a transition metal such as gold is rapid in silicon due to the host lattice having large open interstitial sites. And I particularly talked about gold and silicon in class. But silicon is very open. It's about 74–75% the lattice is open. The equilibrium concentration of vacancies in a crystal is independent of temperature. That's false. It obeys an Arrhenius relation. In polycrystalline materials, grain boundary diffusion often dominates the diffusion process. That is true. Oftentimes, those grain boundaries, which can be very open, allow for rapid diffusion of atoms. Twin boundaries have few broken bonds. They're very idealized interfaces. Imperial diffusion occurs more rapidly in low-density crystal structures. This is impurity diffusion, so if you have a large open structure, you have lots of spaces for things to pass through. Again, coming back to this example of gold in silicon. True or false, ionic compounds bond due to charge transfer between the species. That's true. Just basic chemistry. Self-diffusion occurs slower in covalently bonded materials. And this is self-diffusion in particular because we talk about self-diffusion, so the atom has to break a bond in order to move, and covalently bonded materials are bonded stronger, which means it takes more energy to break and diffusion will occur slower. FCC or BCC crystal structures have a lower packing atomic density. Well, FCC is closed packed. It has a much higher atomic packing factor than BCC. Metals with a higher melting temperature tend to have a lower rate of self-diffusion. And that's because if something has a high melting temperature, the bonds are stronger. If the bonds are stronger, then that means that it's harder to break the bonds to get atoms to diffuse, which means self-diffusion is going to be lower. In FCC crystals, the 111 planes have a higher planar density than any other plane. I put in the 101, but these are the closed pack planes. They're the tightest packed planes in FCC. True or false? Self-diffusion is unimportant for controlling material properties. That's false. Self-diffusion is extremely important. Low-angle grain boundaries are comprised of stacking faults. The angle is the angle of disregistry between the planes. So if there's a small amount of disregistry, we can represent that as dislocations. Fick's second law assumes the diffusion process is independent of position. If you look at the diffusion coefficient, it's just a value. It does have a temperature dependence, but not positional. Arrhenius or power law described phenomena that had discrete energy barriers. Arrhenius, we talked about that in class multiple times. If you have to have something which hops, you have an activation energy, and that fits in that the Q in your activation energy for the Arrhenius relation. Atomic bonds near dislocations are strongly strained. Dislocations introduce very strong strains which have impact not only on mechanical properties but also on point defects which get attracted and trapped by the strain fields. Amorphous materials have short range order but no long range order. Vacancy mechanisms are much faster than direct exchange because these vacancies allow atoms to hop into a vacancy site without having to actually switch places with an atom. They're just switching with a hole in the lattice. Edge dislocations introduce an extra half plane of atoms to the crystal. The screw ones do not. They are just a shear to the lattice. And the ability of an impurity atom to sit interstitially strongly depends on the relative size. Absolutely. And you remember that from chapter 4. Basically, the interstitial sites are relatively small, so they have to have a species of a certain size or less than a certain size. And that is part 9. So that was Exam 1 of MSE201 Spring 2017.